Hi everyone. In this video, I will be demonstrating how to perform a second order factor analysis using the lavaan package with RStudio. So the path diagrams or the diagrams that you see on your screen right here, these were drawn up actually using the Stata SEM builder. These actually look nice enough that I thought I would go ahead and continue using these just to kind of visualize the models that we're going to be running through lavaan. So the model on the left is essentially a first order factor model. Basically, we have four factors, and those factors are being proposed to account for the interrelationships among a set of items or indicators associated with a coping styles questionnaire. So you'll notice that we got arrows pointing from problem solving to P1, P2, P3. Those are indicators of the problem solving factors. So the indicators are measured variables. Those are the variables that we actually have data on. And all of these are essentially associated with a given questionnaire item from this coping styles questionnaire. So we have problem solving with P1, P2, P3 serving as indicators. We have cognitive restructuring with C1 through C3 serving as its indicators. We have express emotion with E1 through E3 as its indicators, and then social support with S1 through S3 serving as its indicators. So you'll notice in that first order model that we have double-headed arrows connecting the latent factors or latent variables, if you will. And so all of these associations are allowed to be freely estimated. Now, within this model, the basic idea is that we're trying to account for the relationships among a set of manifest variables or observed variables by way of proposing this factor solution. So we're proposing that these four factors will do a good job of accounting for the interrelationships among those variables. Now, on the right, we have a second order factor model, and you'll notice that we still have relationships specified between the first order factors and their respective indicators. So all that's the same, but the differences come in that now we have second order factors. So the second order factors are proposed to account for the interrelationships among the first order factors. So you'll notice that we've got over here, we've got problem focused coping. That's the second order factor. With that factor, with an arrow drawn from it to problem solving, the first order factor right here. Then we also have problem focused coping with an arrow drawn to cognitive restructuring right here. So both of these first order factors are proposed. The relationship between those first order factors is proposed to be accounted for by the second order factor, which is problem focused coping. Then when we look at express emotion and social support, those being the first order factors, that association is proposed to be accounted for by this emotion focused coping second order factor. You also notice that we have a correlation or covariance drawn between the two second order factors. Now in our model, you'll see the ones on some of these paths within our first order model and our second order model. And basically what those are doing is setting a measurement scale for latent factors within the model, because in the latent factors don't have an inherent measurement scale. So we have to essentially assign one. And so there's a couple of ways that we can do that. One way is to fix a factor loading to 1 for each factor in relation to a marker variable. And so that's one way. So we're essentially scaling the latent factors in relation to an indicator variable. And then an alternative way would be to set the measurement scale for the latent factors just by fixing the variance to 1. So that's two ways to do this. So in this particular set of models right here, we are essentially setting the measurement scales in relation to a marker variable. In the model, in our first order model, you'll see that with respect to the problem solving factor, we're setting its variance in relation to P1. Then for cognitive restructuring, we're setting its variance in relation to C1. Then for express emotion, we're setting its variation or variance in relation to E1. And then social support, we're setting its variance in relation to S1. And that's that holds up in our second order factor model over here. So it's going to be the same thing. And in both of those models, then those factor loadings are not estimated because they're fixed. So the remaining factor loadings, however, are freely estimated within this model. You'll notice that within the second order factor model that we've got two coefficients right here that are fixed to 1. And so we're setting the measurement scale of the second order factors in relation to those first order kind of marker variables, if you will, or latent marker variables. And then we're freely estimating the other path right here within our paths right here within our model. So as we go through this video presentation, what we're going to do is we're going to start out by specifying the one factor model using lavaan. We'll test it out. We'll look at its goodness of fit, and then we'll proceed to specifying the second order factor model. So you can see a little bit of the difference in the syntax between the two models. And so we'll look at that, the fit of that model as well. And then we're going to compare the two models in terms of their fit. So as you're looking at these two models, you might get the idea that maybe the model on the right is more complicated than the model on the left. But in fact, the model on the right is actually a more simplified model in relation to the model on the left. The model on the left actually estimates more parameters. And so that by virtue of that, we are this model would be a more complicated representation of the relationships among our observed variables, whereas the model on the right, we're actually estimating fewer parameters because we're imposing some restrictions. And so in that particular case, it's actually a more parsimonious representation of the relationships among our measured variables. Now, what happens in terms of kind of the unrestricted model on the left and the restricted model on the right is that typically the unrestricted model is going to fit the data better than a more restrictive version of that model. And so what we would expect is that when we have these two models, one being kind of a more restrictive version of the other, we would expect the unrestricted model to fit better than the more restrictive version. Now, the question is, do these two models fit differently enough that we would say that the model on the right, the second order model, is actually a significantly worse fit to the data than the model on the left. And that's where we can utilize a chi-square difference test in order to test that out. So in this video presentation, we'll test out both of these models. We'll look at them separately. I'm not going to go into all details behind it, but we'll look at them kind of separately. Then what we'll do is we're going to use a likelihood ratio test in order to test the difference in fit between these two models. And then we'll also reference the information criteria indices associated with both of these models as well in order to further ascertain differences in fit. So now let's go ahead and open up RStudio. So here we are, and what we will be doing is basically running our analyses. These two models are kind of derived in part from a presentation by Tim Brown in his book on confirmatory factor analysis. Now, it just so happens that the data in his book, or at least the 2006 version of his book, was in summary form. So in other words, you had correlations and standard deviations for your variables. So we're not actually going to work with the raw data itself. We're going to utilize the summary data in running our analysis. But that also means that we have to import that summary data or create a variance covariance matrix using that summary data, which then gets imported into lavaan for running our analysis. So in terms of our discussion right here, you'll see I've got a little text file that I will make available underneath the video description, so you can download this. And what I'll be doing, I'm not going to type in everything directly. I'm just going to walk through this text file and discuss various parts of the code so that you can get a better understanding about what's going on. And then what I'll do is I'll copy it and paste it into the console in RStudio and run the analysis that way. I just find that oftentimes using text files, doing the heavy lifting, so to speak, by typing everything into the text file is more efficient than trying to kind of go bit by bit using the command prompt in RStudio. So if you haven't already done so, you'll need to make sure, obviously, to have lavaan installed, and we're also going to utilize, just kind of to visualize the CFA models, we'll use the SEMplot package, and we'll just again to visualize. We're not going to go into all aspects of the plot or using the function, the SEM paths, with this particular package, but just to kind of visualize things a little bit more in detail. And certainly you can consult various options associated with that later on. So as you can see in this text file right here, I've got just install.packages. Inside the quotation marks, I have SEM plot with the capital P right there. So in order to install it, you just basically, I'm just going to copy it and paste it in right here. And there you go. It's just going to take a second, and it's installed. And then we will use the library function to call up both lavaan and SEMplot. So as you can see right here, I've just typed library, the library function inside the parenthesis, lavaan, the same for SEMplot. So I'll copy both of those and put them in here as well. And so now basically both of those packages are available and ready to go in terms of running our analysis. But again, before we do that, we need to get the data into a form that will allow us to run our analysis. So again, we don't have raw data. So as you're looking at this this text file right here, you'll notice that what I have right here is I'm creating an object that is called lower, and it's going to contain the correlations among my my variables for this particular scale. So I have lower followed by a less than sign and a hyphen, which produces an arrow, obviously. And then I've got an initial single quote right here. At the end of the code for when I'm inputting this correlation matrix, I have also a single quotation mark. So everything else in between are the correlations among the variables. So the ones are the principal diagonal for the correlation matrix. On the off diagonal, you have the correlations among the items associated with this particular survey or questionnaire. So then down below, you'll see that I've got, I'm creating a new object that's going to contain the full symmetric matrix. So right now, well, all we have is the principal diagonal and the lower triangle for this matrix. And what we want to do is to create a symmetric matrix where the values that are shown, that are displayed below the principal diagonal containing the ones, are the same above the principal diagonal in their respective positions. So you'll notice that this object that I'm just going to call it cormat, C-O-R-M-A-T, for lack of a better way of naming it. You'll notice that I've got an arrow pointing to it, and then we're using this get cov function. So the C right here is in caps. And just kind of keep in mind that, you know, this is basically get a covariance matrix. If we had a variance covariance matrix where instead of the correlations, we would still be using this function to create a symmetric matrix. But with a correlation matrix, just kind of keep in mind that a correlation matrix is nothing more than a matrix containing covariances among a set of standardized variables. All of them having a mean of 0 and a standard deviation of 1. So this is still applicable in this demonstration. So we've got the get cov function followed by a reference to our object containing the correlation matrix, which is lower, then a comma followed by names equals. And so we're using the concatenate function. And inside the parenthesis, we have the names of all of our observed variables separated by quotation or with quotation marks around them and separated by commas. So as you can see, then we have to have an end parenthesis that closes out this function right here, and then we have another end parenthesis which closes out our function for get cov. So once we've done that, then once we've run this part of our code, then we end up with an object called core_mat. And if I just type this in, I'll see the correlation matrix, the full symmetric correlation matrix with the variable names associated with it. So let's go ahead and do this. We're going to go ahead and highlight all of this, and I will just kind of copy that, and I'll paste it in and hit enter. And so now you can see that we have our correlation matrix. So you see along the principal diagonal that contains the ones that you see right here, and then on the off diagonals we have the corresponding values in the lower triangle and the upper triangle of that particular matrix. So now we've got a full symmetric correlation matrix. So the next issue then is to construct our variance covariance matrix. So what we'll need are the standard deviations. So right here, I'm creating an object called SD with an arrow pointing to it. And again, we're using that concatenate function where I have the standard deviations of our variables in the order in which they appear in the correlation matrix. So all of those are separated by commas. And notice that we're not using quotation marks in this case. We're just typing in the values directly. So when we do that, once we've created this vector of standard deviations, we can use that as an input into this function down here, along with our core_mat object, in order to generate the full variance covariance matrix. So here you'll see I'm creating an object called cov_mat, or COVMAT, and I've got an arrow pointing to it. And then we're using the core_to_cov function that's associated with lavaan. And there aren't any caps right there, but you'll notice that the first position right here, the first argument, we are referencing the correlation matrix that we created above, as well as the vector of standard deviations right there. So if I type this in after running the previous code, that will demonstrate the full variance covariance matrix. So I'll go ahead and highlight both of these and copy it and paste it in so you can see. And looks like there was a bit of an error right here. And actually the error was quite simple. I had failed to create my vector of standard deviations. You can type it into your text file, but unless you actually run it in our RStudio, it's not going to work. So I needed to highlight all three of these lines right here, and then we'll copy it and paste it in. And so now we have our variance covariance matrix. So the values on the principal diagonal right here, these are the variances associated with each of our indicator variables, and then on the off diagonal, those are the covariances for those variables. So now we're ready to run the first order factor model. So as you can see, by the way, the pound signs in RStudio just are used for comments. So I just kind of created a little comment right here. If you were running this as a batch, that's what's going to happen. So it's going to ignore the comments. You'll see them in the output, but it's not going to do anything with it. So the first thing that we need to do then is we need to create an object for this first order factor model that contains the model information. So I'm creating an object. I'm just going to call it first order. You'll notice that we have an arrow, and then we have a single quote here. At the end, we also have a single quote. So it's the same structure that we had created when we formed this lower object right here. We had the object name, arrow, and then we had the single quotes starting off with before we input our information, and a single quote afterwards after we've input the information. So our model information is contained between those two single quotes. As we're looking at it, you can see that I've got I'm naming my factors problem solve, and then I've got an equal sign followed by a tilde. So make sure that you have an equal sign followed by a tilde when you are specifying your factor model. If you just have a tilde only, then you're essentially specifying a regression. So you don't want to do that. You want to make sure you have an equal sign followed by a tilde. And then on the right-hand side, we've got the indicators that are separated by a plus sign. So those P's, the P1, P2, P3, all of those are variables that we've named and are associated with the covariance matrix that we just generated. Then we have the cognitive restructuring factor that I'm creating right here, followed by equal sign tilde, and then we've got the C1 plus C2 plus C3. Express emotion right here, that factor, we have an equal sign tilde, E1, E2, E3, all separated by plus signs, and then social support, equal sign tilde, followed by S1 plus S2 plus S3. So when we run this part of our syntax, we are saving that model information to an object that's called first order, and then we use that object as an input into our function where we are actually running our analysis. So the function that we're going to be using is the CFA function associated with lavaan. And you'll see inside the parenthesis, the first argument is referring to our model. So that's just referencing the first order that we just specified up here. Then we have a comma followed by sample.cov, and I have set this equal to COVMAT, the covmat object that we created. So that contains our variance covariance matrix. So we have to type in again sample.cov equals covmat. And then we have a comma, and then we have another argument, sample.nobs, and we set that equal to the sample size. So one thing to keep in mind is that if we were running our analysis from raw data, we would not be using these two arguments right here. We would be using the data argument and referring to the data frame that contains our variables. So that is a difference between what you're seeing here and what probably most of the time you're going to be doing, which is referring to data as it's stored within a data frame. But if you're using summary data, then this is where you're going to be referring to the sample covariance matrix and the sample size directly right here. So the last part of this, you'll see all of this, we have an arrow pointing from it to an object that I'm calling fit first. And so the object is going to contain the information from our fitting of this model. And then what we will use is a summary function down below in order to generate our summary information in terms of the model fit indices and parameter estimates and so forth. So you'll see summary, and we are referring right here, fit first, we're referring to this fit object right here. So I have fit first, comma, and then I've got some arguments that I typically prefer to include, which are fit.measures, and I'm going to set that equal to true. So fit.measures, that's going to get me a larger array of fit indices in my output than if I didn't include that. So I've typed in fit.measures, set that equal to true. Then R square equals true. So if I want the communalities for the first order, for the indicators associated with my first order factors, well, the communalities is a proportion of variation accounted for in the indicators by their respective factors. And so so we can request the R square in order to obtain that. So we have R square set equal to true. And then if you want standardized estimates, which typically when you are reporting on factor analysis, typically that's what people end up reporting on. So in this case, I've typed in stand, set that equal to true. So if I highlight all of this, and I'll even highlight the comment up here just for the demonstration, I'll copy this and I'll paste it in and then run it. So now I have all of my output for this model. And you can see that up here at the top in this area, we've got the chi-square goodness of fit test. So this is a test of the exact fit hypothesis. Basically, the null is that these model implied covariance matrix and the sample covariance matrix are equivalent to each other. So if this is significant, that's actually indicating a lack of fit of our model to the data. But you're essentially rejecting the exact fit hypothesis in this particular case. Now, when we look at the next set of fit indices, we've got the CFI and TLI right here. So these values theoretically range between 0 and 1. There can be some values can sometimes fall outside of that range, but the theoretical range is 0 to 1. The closer to 1, the better. And so values that are above 0.90 would be regarded as at least acceptable, and values that are above 0.95 are typically regarded as, kind of optimal or more superior in terms of the fit of the model. So both of those are indicating quite good fit. We also have our RMSEA index. So the RMSEA right here for our model is 0.051. Values that fall between 0 and 0.05 are typically regarded as evidence of close fit of the model to the data. Values that fall between 0.05 and 0.08 typically are acceptable. Values between 0.08 0.10 are regarded more as kind of mediocre in terms of fit, and then values above 0.10 would be signaling poor fit. So in this case right here, we're right around kind of the upper bound of what would be typically regarded as close fit. In terms of, we also have a p-close test right here. That's a p-value. If this is statistically significant, then that would indicate that our model is fitting significantly. I guess you could say worse relative to what we would expect with a close fitting model. So in that case, it's more about testing the close fit hypothesis. So if this is not significant, then that would be regarded as an indication that our model is, demonstrating more of a close fit to the data. Then we have the SRMR value right here, 0.017. And so values that fall between 0 and 0.05 are typically regarded as evidence of good fit, with values of 0 indicating perfect fit. Values between 0.05 to 0.10 would still be considered acceptable. So we'll scroll down a little bit further and we'll look at the more specific aspects in our model. So looking at, you'll see over here, we've got latent variables. So these are the factors, our 4 first order factors. You'll notice that they also give you they show you kind of in terms of what we typed in code, the equal sign followed by the tilde. So these are the indicators of those factors right there. The estimate column right here contains unstandardized estimates with the caveat that the first indicator associated with each of those latent variables, the factor loading is fixed to 1. So you have estimates and significance tests associated with the remaining loadings, whereas that first loading associated with each of those factors, that is not tested because it's fixed. If you look in this column right here, this is for these are the estimates associated with a fully standardized solution. And you can look at, you'll see that you have estimates for all of the indicators associated with a factor. And that's because in this solution right here, we fixed the factor variance to 1. And so now we can estimate the parameters associated with basically the factor loadings associated with the indicators there. So these are all going to be correlations between the indicator variables and their respective latent factors. So that's what we're seeing in this column over here. So all of those values, though, are quite high, which is a good thing. When we scroll down a little bit further, we have the covariances among our first order factors. So in the estimate column right here, these are the covariances among those first order factors. We have significance tests testing those covariances right there. If you look in the this last column right here, you can interpret these as correlations among those first order factors. So you can see that on the low side, we've got a correlation of 0.196. On the high side, we've got a correlation of 0.67. When we scroll down a little bit further, you can also see we have variance estimates that are given. So basically, we have measurement error variances, or the variance for the uniquenesses for each of our indicator variables. These are all given all the way down here for each of those indicators. Then we've got the variances of the 4 first order factors, which are given right here. So that's those right there. If we scroll down a little bit further, you'll also see that we have R-square values. So the R-square values are basically reflecting the proportion of variation in the indicator variables that's accounted for by the factors in the model. Because each indicator is associated with a single factor, then you can essentially attribute the variance accounted for to that single factor. So these are basically communality estimates for each of our indicator variables. I will point out too, one other thing that going back to that last section where we had our factors and the variances estimated right there, in the fully standardized solution, you can see that these variances were all fixed to 1, so which we would expect. So that's basically a rundown of the first order factor model. So now let's change things up a little bit, and we'll specify the second order factor model. Actually, one other thing I did earlier on, I did indicate that we would be using that SEM plot package. So the function associated with that package that we're going to use is SEM paths with a capital P in there. So SEM paths, you'll see that in the first position right here, we've got fit first. So that's referring back to this fit object right here, comma, and then I've got what equals, and then inside the parentheses here, I've got stand. So in this diagram that's going to be created, we're going to be generating standardized estimates. They'll show up in that model. And then I've got layout equals tree with quotation marks surrounding tree. So to see what this looks like, I'll copy it and paste it in, and we'll hit enter. And so now you can see to the right, we have our model. So as you can see right there, it contains our standardized estimates. And you can see we have our, basically just different components of our model. Without getting into all the details, there are ways to maybe make this look a little bit more attractive. Usually I don't spend my time on that particular issue so much. I'm more interested in actually, developing models and running them and so forth. And so usually I draw things out using other programs. But as you can see right here, that's just a visualization of our first order factor model. You'll see in the very light greens at the top associated with each of those factors, you'll see the double-headed arrows. Then you'll see also down at the bottom, there's double-headed arrows associated with each of the indicator variables. And the values down there are going to be the basically be, the variances associated with each of the indicators, or excuse me, error variances associated with the indicators. So that's just kind of a quick visualization. If you want to learn more about that, certainly consult the package, the SEM plots package, and there are alternative approaches that might give you something that looks a little bit more attractive than that. So then we'll move on. We'll specify our second order factor model. And for this model, I'm going to create a new object name called second order. We have our arrow followed by the single quote. We have our single quote at the end. And in this case, I've added some comments just to help facilitate, remembering where things are at. So the first comment, I just am specifying the first order factors. So all of this part right here is exactly the same as what we had with our first order factor model. Then you'll see that I've got a comment specification of the second order factors. And so I've got problem focused equals to, followed by a tilde, followed by problem solving plus cognitive restructuring right there. So in this case right here, I am referring to the first order factors that are being used to as indicators of problem focused coping, which is the second order factor. Then I've got the emotion focused second order factor, equals sign followed by a tilde, followed by the express emotion and social support first order factors. So again, with these two factors right here, these second order factors, I'm referencing back to the first order factors. So that's the way to kind of think about it. So then I'm creating a new fit object. I'm calling it fit sec. And then we are referencing in this first position right here, second order. And then everything else is exactly the same. We're just applying the CFA function in lavaan, and we're generating our output based on this new model specification, which we had laid out right here. You'll see that for the summary, then we're going to reference that fit sec object right there, and everything else I'm leaving the same. And for the SEM paths, we're also going to leave fit sec the same in this. So now what I'll do is I'll highlight all of this and I'll copy and I'll paste it in so we can take a look at it. So now on the right, you see the second order factor model. So in this case, you can see the correlation between the second order factors is 0.3. You'll see that, and basically this is our standardized solution. So the loadings that you see, basically where the factors are being connected to their respective indicators, all those are the correlations I was telling you about, which was in that last column of the output. So if you look like right here, I'll kind of scroll back up. You'll see that we've got this, the standardized all right here. So if we talk about the relationship between the first order factors and their indicators, you'll see that we've got, it's kind of hard to read right here, but you'll see right here we've got the 0.911, that's this value right here. Then we've got the 0.864, that's this value right here. 0.879, that's this value right here. So these are the correlations between the indicators and the first order factors. If we scroll down a little bit further, what you'll see are the correlations between the second order factors and the first order factors. So you'll see right here, we've got, let me see if I can find it here. We've got the 0.812, which is the loading for the problem solving factor with the first order factor problem solving and the problem focus factor. So the 0.812 is this loading right here. Then we've got problem focus with cognitive restructuring right here. So that number, that's a 0.82 right there. Then we've got emotion focused as our second order factor. The first order factors are express emotion 0.826. This is rounded off at 0.83, and then we've got 0.812 for the social support, and you can see right here it's 0.81 rounded off there. So that, that's based, those are the estimates that are shown in the figure on the right. So then what we'll do is we'll go ahead and scroll back up. We'll take a look at the overall fit of the model. So looking at the chi-square goodness of fit test, you can see that we've got the chi-square value is 83.005. Degrees of freedom for the model is 49, and we see that we have statistical significance, which would lead us to reject the exact fit hypothesis. But nevertheless, when we look at the CFI and TLI, those values are quite high and quite good. So that's indicating a good fitting model. When we scroll down and look at the RMSEA, we have our 0.050. It's actually a shade better than what we had with our previous model, which would be consistent with a close fitting model. And then our SRMR is also indicating a very good fitting model. So taken all together, we see that with our first order factor model and our second order factor model, in terms of the fit statistics, they're basically indicating good fit for both of these models. The chi-square values are, in particular, are really not very different from each other. And the other fit statistics really are quite similar to each other as well. But what we can do, actually, I'll kind of scroll down a little bit further just to show you too. We've got the covariance between problem focus and emotion focus coping right there. That's the covariance. There's the standard. There's the significance test. So they're positively related to each other, and you can also see that we've got the correlation between those two factors given there. As we scroll down a little bit further, you can see that we've got the variance estimates for the uniquenesses, as well as the variance estimates associated with basically the measurement error variances associated with the first order factors. And then we've got the variance estimates for the second order factors given here. In terms of the R-square values, we've got our communalities for each of our indicator variables in relation to those first order factors. And then we've got the basically our R-squares for the second order, the first order factors in relation to the second order factors. So you can see that we are accounting for, with those second order factors, accounting for between about 66% of the variance in a given factor and 68% of the variance in a given factor. So there you go. So now we're going to kind of do a model comparison. Really, again, the models look like they're largely fitting the same. But the question is ultimately, which model do we prefer? Which one do we want to go with? And as I said earlier on, the less restrictive model, the first order factor model is less restrictive than the second order factor model. The second order factor model is actually a more parsimonious representation of the interrelationships among the measured variables in our data set. And so what we would have is a situation where the fit, even though the more restrictive model might fit worse, ideally that fit is not significantly worse than the unrestricted model. And so if that's the case, then we would prefer the second order model because we're estimating fewer parameters in that model. It's a simpler model than the unrestricted model. So to do that, we can use the basically a likelihood ratio chi-square test, where we're testing the difference in the chi-square values between the two models. So in a nutshell, if we kind of go back up here, we've got our chi-square value right here for our second order model. It's 83.005. If we go back to the first order model, the chi-square was 82.97. It's a little bit smaller than the chi-square for the second order model. And in terms of carrying out the test, we're just computing the difference in those chi-square values, taking the chi-square for the unrestricted model, the restricted model, and subtracting the chi-square from the unrestricted model. And the degrees of freedom for that test is the difference in degrees of freedom between the two models. So there's a nice little command in lavaan that will allow us to carry out our test. So I'll kind of scroll down here, and that command is lav test LRT. Now, make sure that you capitalize the T and you capitalize the LRT. Okay, so if you don't do that, it's not going to work. So in this case, I'm using the lav test LRT, and inside the parenthesis, I have the fit object from our first order model and the fit object from our second order model. So these are not the models themselves. These are the objects that contain the information after we've estimated both of those models. So just kind of keep that in mind. So when I copy this and I'll paste it on in and hit enter, now you can see that we've got our test results. So down at the bottom, it may be a little tricky to see, but you'll notice that we've got a reference to the fit first model, and you can see right here the degrees of freedom is 48. There's the chi-square value from that model right there, which we've already seen. Then we've got the second model, a second order factor model with 49 degrees of freedom, and the chi-square value down here of 83.005. So the chi-square difference between these two models is 0.034783. So the question is that difference statistically significant? And would that, if it is significant, then that would lead us to prefer the first order model as opposed to the second order model. So you'll see in our output here, we've got the degrees of freedom difference, which is 1. And you can also see too that we've got the p-value, which is 0.8521. So there's not a significant difference between those two models, which would lead us then to essentially prefer that second order model that fits maybe a slight bit worse, at least using the chi-square value, than the first order model. But that difference is not substantial enough to justify sticking with the less parsimonious model, which is that first order model. You'll also see too in the output, you've got these information criteria. You've got AIC and BIC right here. That's the Keiki's information criterion, and BIC is Bayesian information criterion. And you can use these indices for model comparison as well. So not just necessarily relying on a significance test, but also testing whether but also just kind of looking at the relative fits of these models. And the basic idea is that these two indices take into account model complexity, parsimony of the model, and you can't use them by themselves in order to evaluate the fit of a single model, but you can use them for comparative purposes. Now, these indices generally are utilized in most cases with models that are not nested, but you can use them with nested models, such as these two models that we're working with, in order to make a judgment about which model fits the data better, or which model fits the data best, so to speak. Now, in terms of using these, essentially the model that, if I'm comparing two models, the model that has the lower AIC would be the preferred model. And the same goes for the BIC. Now, it is important to kind of keep in mind, too, that these indices don't always lead to the same conclusion, but for our current demonstration, they actually do. So if we're looking at the AIC and BIC of our models, for the one-factor model, the AIC is 11,346. For the second order factor model, actually it should have said first order factor model, it's 11,346. For the second order factor model, it's 11,344. That number for the second order model is lower than the number for the first order model, supporting the use, or supporting going with the second order factor model. The BIC, we have, in this case right here, we've got 11,454 for the first order factor model versus 11,448 for the second order factor model. So again, the BIC is lower for the second order factor model. So both of these indices then would support sticking with the second order factor model as compared with the first order factor model. So that's going to basically wrap up this video demonstration. Check underneath the video description. There'll be a link to the text file, and there you go. So I really appreciate you watching, and you guys have a great day.